Hey, this is Lance from LangChain. I wanted to talk to a recent paper that I saw called Adaptive RAG, which brings together some interesting ideas that have kind of been covered in other videos, but this actually ties them all together in kind of a fun way. So the two big ideas to talk about here are one of query analysis. So we've actually done kind of a whole RAG from scratch series that walks through each of these things in detail, but this is a very nice example of how this comes together with some other ideas we've been talking about. So query analysis is typically the process of taking an input question and modifying it in some way to better optimize retrieval. There's a bunch of different methods for this. It could be decomposing it into sub-questions. It could be using some clever techniques like step-back prompting. But that's kind of like the first stage of query analysis. Then typically you can do routing. So you route a question to one of multiple potential sources. It could be one or two different vector stores. It could be a relational DB versus a vector store. It could be web search. It could just be like an LLM fallback, right? So this is like one kind of big idea. Query analysis, right? It's kind of like the front end of your RAG pipeline. It's taking your question, it's modifying it in some way, it's sending it to the right place, be it a web search, be it a vector store, be it a relational DB. So that's kind of topic one. Now topic two is something that's been brought up in a few other videos of what I kind of call flow engineering or adaptive RAG, which is the idea of doing tests in your RAG pipeline or in your RAG inference flow to do things like check relevance documents, check whether or not the answer contains hallucinations. So this recent blog post from Hamil Hussein actually covers evaluation in some really nice detail. And one of the things he highlighted explicitly is actually this topic. So he talks about unit tests, and in particular he says something really interesting here. He says, unlike typical unit tests, you want to organize these assertions in places beyond typical unit testing, such as data cleaning, and here's the key point, automatic retries during model inference. That's the key thing I want to draw your attention to. It's a really nice approach. We've talked about some other papers that do that, like corrective RAG, self-RAG, but it's also cool to see it here and kind of encapsulated in this way. The main idea is that you're using kind of unit tests in your flow to make corrections. Like if your retrieval is bad, you can correct from that. If your generation has hallucinations, you can correct from that. So I'm going to kind of draw out like a cartoon diagram of what we're going to do here. And you can kind of see it here. We're starting with a question. We talk about query analysis. We're going to take our question and we're going to decide where it needs to go. And for this particular toy example, I'm going to say either send it to a vector store, send it to web search, or just have the LLM answer it, right? So that's like kind of my fallback behavior. Then we're going to bring in that idea of kind of online flow engineering or unit testing, where I'm going to have my retrieval, either from the vector store or web search. I'm then going to ask, is this actually relevant to the question? If it isn't, I'm actually going to kick back to web search. So this is a little bit more relevant in the case if I've routed to the vector store, done retrieval, documents aren't relevant, I'll have a fallback mechanism. Then I'm going to generate. I check for hallucinations in my generation, and then I check for whether or not the generation actually answers the question. Then I return my answer. So again, we're tying together two ideas. One is query analysis, like basically taking a question, routing it to the right place, modifying it as needed, and then kind of online unit testing and iterative flow feedback. So to do this, I've actually heard a lot of people talk online about Command R, a new model release from Cohere. It has some pretty nice properties that I was kind of reading about recently. So one, it has nice support for tool use, and it does support query writing in the context of tool use. So this all rolls up in really nice capabilities for routing is kind of one. Now two, it's small. It's 35 billion parameter. It's actually open weight, so you can actually run this locally, and I've tried that. We can talk about that later. And it's also fast, served via the API. So it's kind of a small model, and it's well tuned for RAG. So I've heard a lot of people talking about using Cohere for RAG, and it has a large context, 120,000 tokens. So it's like a nice combination of properties. It supports tool use and routing. It's small and fast, so it's like quick for grading, and it's well tuned for RAG. So it's actually a really nice fit for this particular workflow where I want to do query analysis and routing, and I want to do kind of online checking and RAG. So kind of there you go. Now let's just get to the coding bit. So I have a notebook kind of like usual. I've done a few pip installs. You can see it's nothing exotic. I'm bringing in LangChain Cohere. I set my Cohere API key. Now I'm just going to set this LangChain project within LangSmith, so all my traces for this go to that project. And I have enabled tracing, so I'm using LangSmith here. So we're going to walk through this flow, and let's do the first thing. Let's just build a vector store. So I'm going to build a vector store using Cohere embeddings with Chroma, open source VectorDB, runs locally, from 3 different web pages on blog posts that I like. So it pertains to agents, prompt engineering, and adversarial attacks. So now I have a retriever. I can run retriever invoke, and I can ask a question about, agent memory. Agent memory. And there we go. So we get documents back. So there we go. We have a retriever now. Now, here's where I'm going to bring in Cohere. I also want a router. So if you look at our flow, the first step is this routing stage, right? So what I'm going to do is, I'm guessing going to find 2 tools, a web search tool and a vector store tool, okay? In my preamble, is just going to say you're an expert routing user questions to vector store or web search. Now here's the key. I tell it what the vector store has. So again, my vector store has agents, prompt engineering, adversarial attacks. I just repeat that here, agents, prompt eng, adversarial attacks. So it knows what's in the vector store. So use it for questions on these topics, otherwise use web search. So that's it. I use Command R here. Now I'm going to bind these tools to the model and attach the preamble, and I have a structured LLM router. So let's give this a few tests just to kind of sandbox this a little bit. So I can here's my chain. I have a router prompt. I pass that to the structured LLM router, which I defined right here. And let's ask a few different questions, like who will the Bears draft in the NFL draft? What are the types of agent memory? And hi, how are you? So I'm going to kick that off. And you can see, it does web search, it goes to vector store, and then actually returns this false. So that's kind of interesting. This is actually just saying if it does not use either tool, so for that particular query, web search or the vector store was inappropriate, it'll just say, hey, I didn't call one of those tools. So that's interesting. We'll use that later. So that's my router tool. Now the second thing is my grader. And here's where I want to show you something really nice that is generally useful for many different problems you might encounter. So here's what I'm doing. I'm defining a data model for my grade. So basically, grade documents, it's going to this is a pedantic object. It is just basically a binary score here, field specified here. Documents are relevant to the question, yes, no. I have a preamble. Your grader assessing relevance of retrieved documents to a user question, blah, blah. So, and then basically give it a binary score, yes, no. I'm using Command R, but here's the catch. I'm using this with structured outputs thing, and I'm passing my grade documents data model to that. So this is the key thing. We can test this right now as well. It's going to return an object based upon the schema I give it, which is extremely useful for all sorts of use cases. And let's actually zoom back up. So we're actually right here. So this grader stage, right, I want to constrain the output to yes, no. I don't want any preambles, I don't want anything, because the logic I'm going to build in this graph is going to require a yes, no binary response from this particular edge in our graph. So that's why this grader tool is really useful. And I'm asking a mock question, types of agent memory. I do a retriever. I do a retrieval from our vector store. I get the tuck and I test it. I invoke our grader, retrieval grader chain with the question, the doc text, and it's relevant as we would expect. So that's good. But again, let's just kind of look at that a little bit more closely. What's actually happening under the hood here? Here's the pedantic object we passed. Here's the document in question I'm providing. Basically, it's converting this object into Cohere function schema. It's binding that to the LLM. We pass in the document question. It returns an object, basically a JSON string, per our pedantic schema. That's it. And then it's just going to parse that into a pedantic object, which we get at the end of the day. So that's what's happening under the hood with this with structured output thing. But it's extremely useful. And you'll see we're going to use that a few different places. Because we want to ensure that in our flow here, we have 3 different grading steps, and each time we want to constrain the output to yes, no. We're going to use that structured output more than once. This is just my generation. So this is good old RAG. Let's just make sure that works. I'm using a RAG chain, typical RAG prompt. Again, I'm using cohere for RAG, pretty easy. And yeah, so the RAG piece works. That's totally fine. Nothing too crazy there. I'm going to find this LLM fallback. So this is basically if you saw our router chain, if it doesn't use a tool, I want to fall back and just fall back to the LLM. So I'm going to kind of build that as a little chain here. So, okay, this is just a fallback. I have my preamble, just you're an assistant, answer the question based upon your internal knowledge. So again, that fallback behavior is what we have here. So what we've done already is we defined our router piece. We've defined our basic retrieval, our vector store we already have here. We've defined our first logic or like grade check, and we defined our fallback. And we're just kind of roll through the parts of our graph and define each piece. So I'm going to have two other graders, and they're going to use the same thing we just talked about. Slightly different data model. I mean, same output, but actually just slightly different prompt and description. In this case, it's the answers grounded in the fast yes no. This is my hallucination grader, and then I have an answer grader as well. And I've also run a test on each one, and you can see I'm getting binary. These objects out have a binary score. So there's a pedantic object with a binary score, and that's exactly what we want. Cool. And I have a search tool. So that's really nice. We've actually gone through and we've kind of laid out, I have like a router, I've tested it, we have a vector store, we've tested it, we've tested each of our graders here. We've also tested generation of just doing RAG. So we have a bunch of pieces built here. We have a fallback piece, we have web search. Now the question is, how do I stitch these together into this kind of flow? And for that, I like to use LangGraph. We'll talk a little bit about LangGraph versus agents a bit later, but I want to show you why this is really easy to do using LangGraph. So what's kind of nice is I've kind of laid out all my logic here. We've tested it individually. And now all I'm going to do is I'm going to first lay out the parts of my graph. So what you're going to notice here is first there's a graph state. So this state represents kind of the key parts of the graph, or the key kind of objects within the graph that we're going to be modifying. So this is basically a graph centered around RAG. We're going to have question, generation, and documents. That's really kind of the main things we're going to be working with in our graph. So then you're going to see something that's pretty intuitive, I think. What you're going to see is we're going to basically walk through this flow, and for each of these little circles, we're just going to find a function. And these little squares, or these, you can think about every circle as a node, and every kind of diamond here as an edge or conditional edge. So that's actually what we're going to do right now. We're going to lay out all of our nodes and edges, and each one of them are just going to be a function. And you're going to see how we do that right now. So I'm going to go down here. I define my graph state. So this is what's going to be kind of modified and propagated throughout my graph. Now all I'm going to do is I'm just going to find a function for each of those nodes. So let me kind of go side by side and show you the diagram, and then like kind of show the nodes next to it. So here's the diagram. So we have a retrieve node, so that kind of represents our vector store. We have a fallback node, that's this piece. We have a generate node, so that's basically going to do our RAG. You can see there. We have a grade documents node, kind of right here. And we have a web search node, so that's right here. Cool. Now, here's where we're actually going to find the edges. So you can see our edges are the places of the graph that are kind of making different decisions. So this route question edge, basic conditional edge, is basically going to take an input question and decide where it needs to go. And that's all we're doing down here. It kind of follows what we did up at the top, where we tested this individually. So recall, we basically just invoke that question router, returns our source. Now remember, if tool calls were not in the source, we do our fallback. So we actually showed that all the way up here. Remember this? If tool calls is not in the response, this thing will just be false. So that means we didn't call web search, and we didn't call our retriever tool. So then we're just going to fall back. Yep, right here. And this is just like a catch, just in case the tool can make a decision. But most interestingly, here's where we choose a data source, basically. So this is the output of our tool call. we're just going to fish out the name of the tool. So that's data source. And then here we go. If the data source is web search, I'm returning web search as basically the next node to go to. Otherwise, if it's vector store, return vector store as the next node to go to. So what's this web search thing? Well, remember, we right up here define this node web search. That's it. We're just going to go to that node. What's this vector store? You'll see below how we can kind of tie these strings that we returned from the conditional edge to the node we want to go to. That's really it. Same kind of thing here, decide to generate. That's going to roll in these two conditional edges into one. And basically it's going to do if there's no documents. So basically if we filtered out all of our documents from this first test here, then what we're going to do is we've decided all documents are not relevant to the question, and we're going to kick back to web search exactly as we show here. So that's this piece. Otherwise, we're going to go to generate. So that's this piece. So again, in these conditional edges, you're basically implementing the logic that you see in our diagram right here. That's all that's going on. And again, this is just implementing the final two checks for hallucinations and answer relevance. Yep, so here's our hallucination grader. We then extract the grade. If basically there are hallucinations, in this case, the grade actually, yes, means that the answer is grounded. So we say the answer is actually grounded, and then we go to the next step. We go to the next test. That's all this is doing. It's just basically wrapping this logic that we're implementing here in our graph. So that's all that's going on, and let's go ahead and define all those things. So nice, we have all that. Now we can actually go down a little bit, and we can pull. This is actually where we stitch together everything. So all that's happening here is, you see we defined all these functions up here. We just add them as nodes in our graph here, and then we build our graph here basically by basically laying out the flow or the connectivity between our nodes and edges. So, you can look at this notebook to kind of study in a bit of detail what's going on. But frankly, what I like to do here typically, just draw out a graph, kind of like we did up here, and then implement the logical flow here in your graph as nodes and edges, just like we're doing here. That's all that's happening. So again, we have like our entry point is the router. This is like the output this is basically directing like, here's what the router is outputting, and here's the next node to go to. So that's it. And then for each node, we're kind of applying, like, we're saying like, what's the flow? So web search goes to generate after, and retrieve goes to grade documents. Grade documents kind of is a conditional edge. Depending on the results, we either do web search or generate. And then our second one, we go from generate to basically this grade generation versus documents in question. Based on the output of that, we either have hallucinations, we regenerate, we found that the answer is not useful, we kick back to web search, or we end. Finally, we have that LLM fallback, and that's also, if we go to the fallback, we end. So what you're seeing here is actually the logic flow we're laying out in this graph matches the diagram that we laid out up top. I'm just going to copy these over, and I'll actually go then back to the diagram and kind of underscore that a little bit more. So here is the flow we've laid out. Again, here is our diagram, and you can kind of look at them side by side and see how they basically match up. So here's kind of our flow diagram going from basically query analysis. That's this thing, this route question. And you can see web search, vector store, LM fallback, web search, vector store. So those are like the three options that can come out of this conditional edge. And then here's where we connect. So if we go to web search, then basically we next go to generate. So that's kind of this whole flow. Now if we go to retrieve, then we're going to grade. So that's it. And, it follows kind of as you can see here. That's really it. So it's just nice to draw these diagrams out first, and then it's pretty quick to implement each node and each edge just as a function, and then stitch them together in a graph just like I show here. And of course, we'll make sure this code's public so you can use it as a reference. So there we go. Now let's try a few different test questions. So like, what player are the Bears expected to draft in the NFL draft, right? Let's have a look at that, and this should print everything it's doing as we go. So okay, this is important. Route question. It decides to route to web search. That's good. It doesn't go to our vector store. This is a current event, not related to our vector store at all. It goes to web search, and then it goes to generate. So that's what we'd expect. So basically, web search goes through to generate, and we check hallucinations. Generation is grounded in the documents. We check generation versus question. The generation addresses the question. The Chicago Bears are expected to draft Caleb Williams. That's right. That's the consensus. So cool. That works. Now let's ask a question related to our vector store. What are the types of agent memory? We'll kick this off. So we're routing. Okay, we're routing to RAG. Now look how fast this is. That's really fast. So we basically whip through that document grading, determine they're all relevant. We go to the decision to generate. We check hallucinations. We check answer versus question. And there are several types of memory stored in the human brain. Memory can also be stored in generative agents. You have LM-powered agents. Memory stream retrieval model and reflection mechanisms. So it's representing what's captured in the blog post pretty reasonably. Now let me show you something else that's kind of nice. I can go to LangSmith, and I can go to my projects. We create this new project, Cohere Adaptive RAG, at the start, and everything is actually logged there. Everything we just did. So I can open this up, and I can actually just kind of look through all the stages of my LangGraph to here's my retrieval stage, here's my grade document stage, and we can kind of audit the grading itself. We kind of looked at this one by one previously, but it's actually pretty nice. We can actually audit every single individual document grade to see what's happening. We can basically go through to, this is going to be one of the other graders here. Yep, so this is actually going to be the hallucination grading right here. And then this is going to be the answer grading right here. So that's really it. You can kind of walk through the entire graph. You can kind of study what's going on, which is actually very useful. So it looks like this worked pretty well. And finally, let's just ask a question that should go to that fallback path down at the bottom, like not related at all to our vector store current events. And yeah, hello, I'm doing well. So it's pretty neat. We've seen in maybe 15 minutes, we've from scratch built basically a semi-sophisticated RAG system that has agentic properties. We've done it in LangGraph. We've done with Cohere Command R. You can see it's pretty darn fast. In fact, we can go to LangSmith and look at, so this whole thing took 7 seconds. That is not bad. Let's look at the most recent one. So this takes 1 second. So the fallback mechanism to the LLM is like 1 second. Let's just look here. So 6 seconds for the initial LangGraph. So this is not bad at all. It's quite fast. It does quite a few different checks. We do routing, and then we have kind of a bunch of nice fallback behavior and inline checking for both relevance, hallucinations, and answer kind of groundedness or answer usefulness. So, you know, this is pretty nice. I definitely encourage you to play with a notebook. Command R is a really nice option for this due to the fact that it's tool use, routing, small and quite fast, and it's really good for RAGs. It's a very nice kind of a very nice option for workflows like this, and I think you're going to see more and more of this kind of like adaptive or self-reflective RAG, just because this is something that a lot of systems can benefit from. Like a lot of production RAG systems kind of don't necessarily have fallbacks, depending on, for example, like you know, if the documents retrieved are not relevant, if the answer contains hallucinations, and so forth. So this opportunity to apply inline checking along with RAG is like a really nice theme. I think we're going to see more and more of, especially as model inference gets faster and faster, and these checks get cheaper and cheaper to do kind of in the inference loop. Now, as a final thing, I do want to bring up a point about, you know, we've shown this LangGraph stuff. What about agents? You know, how do you think about agents versus LangGraph, right? And I think the way I like to frame this is that LangGraph is really good for flows that you have kind of very clearly defined, that don't have like kind of open-endedness, but like in this case, we know the steps we want to take every time. We want to do basic query analysis routing, and then we want to do 3 grading steps, and that's it. LangGraph is really good for building very reliable flows. It's kind of like putting an agent on guardrails. and it's really nice. It's less flexible, but highly reliable. And so you can actually use smaller, faster models with LangGraph. So that's the thing I like about, we saw here Command R, 35 billion parameter model, works really well with LangGraph. It's quite quick. We were able to implement a pretty sophisticated RAG flow really quickly, 15 minutes. Inference time is on the order of like less than, around 5 to 6 seconds. So pretty good, right? Now, what about agents, right? So I think agents come into play when you want more flexible workflows. You don't want to necessarily follow a defined pattern a priori. You want an agent to be able to kind of reason and make open-ended decisions, which is interesting for certain like long horizon planning problems. Agents are really interesting. The catch is that reliability is a bit worse with agents, and so that's a big question a lot of people bring up. And that's kind of where larger LLMs kind of come into play with, there's been a lot of questions about using small LLMs, even open source models with agents, and reliability has kind of continuously been an issue. Whereas I've been able to run these types of LangGraphs with like Mistral or Command R actually is open weights. You can run it locally. I've been able to run them very reproducibly with open source models on my laptop. So I think there's a trade-off. And there's a new Cohere model coming out, I believe Command R Plus, which is a larger model, so it's probably more suitable for kind of more open-ended agentic use cases. And there's actually a new integration with LangChain that support Cohere agents, which is quite nice. So I think it's worth experimenting for certain problems and workflows. You may need more open-ended reasoning, in which case use an agent with a larger model. Otherwise, you can use like LangGraph for a more reliable, potentially, but constrained flow, and it can also use smaller models, faster LLMs. So those are some of the trade-offs to keep in mind. But anyway, I encourage you, play with a notebook, explore for yourself. I think Command R is a really nice model. I've also been experimenting with running it locally with Ollama. Currently, the quantized model is like 2-bit quantized is like 13 billion. 13 gigs. It's a little bit too large to run quickly locally for me. Inference for things like RAG were on the order of 30 seconds. So again, it's not great for a live demo, but it does work. It is available on Ollama, so I encourage you to play with that. I have a Mac M2 32 gig. So if you have a larger machine, then it absolutely could be worth working with locally. So I encourage you to play with that. Anyway, hopefully this was useful and interesting. I think this is a cool paper, cool flow. Cohere Command R is a nice option for these types of like routing. It's quick, good with LangGraph, good for RAG, good for tool use. So have a look and reply anything, any feedback in the comments. Thanks.